Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 11. That's right, 11.11, modeling using sine and cosine functions. Excellent. So over the last 4 or 5 lessons, we've really been working with the sine and the cosine function and various transformations of those two functions in order to describe graphs or to take an equation and understand why its graph looks the way it does. Today, we're going to be hopping into using these functions to model various periodic phenomena. So let's take a look. And let me give you the exact introduction I just did all over again. Model parameters. The sine and the cosine functions can be used to model a variety of real-world phenomena that are what are known as periodic. That is, they repeat over consistent domain intervals. In other words, periods. The key to understanding or interpreting these models is understanding the physical meaning of the various parameters we've explored in the previous exercises. So let's talk about those quickly before we start to jump into the exercises. Sinusoidal model parameters. That's a great word, isn't it? Sinusoidal. So for y equals a times the sine of b times x minus h plus k, and its cosine version, the absolute value of a is known as the amplitude, which is the distance that the model rises and falls above its midline. K is the midline, or the average y value of the model. B is known as the frequency of the model, and it's related to the period p by the equation b times p equals 2 pi. P is the period, and please note that the period does not show up as one of the parameters in the model, but the period is of the sinusoidal model. It's the minimum distance along the x-axis for the cycle to repeat. And finally, h, the most confusing of them all, is the horizontal shift of the model. It's the amount that the parent function has been shifted horizontally. All right, so given all of these, which we've really discussed a lot in the last few lessons, let's do some modeling. Exercise number 1. The tides in a particular bay can be modeled with an equation of the form d of t equals a times the cosine of bt plus k, where t represents the number of hours since high tide and d represents the depth of the water in the bay. The maximum depth of the water is 36 feet, the minimum depth is 22 feet, and high tide is hit every 12 hours. Letter A. On the axes, sketch a graph of this scenario for 2 full periods. Label the points on this curve that represent high and low tide. Fantastic. I've given you all the information you need to sketch this out. So I'd like you to pause the video now, try to sketch it out. If you're a little bit unsure, perhaps maybe sketch in pencil instead of pen. All right, and then we'll go through it. Pause the video now and take a few minutes to do that. Well, please note, right, the x-axis, or better yet, the t-axis in this case, is the time since high tide. In other words, when t is equal to 0, we should have the depth of the water at high tide, which is 36 feet. So I'm going to throw that on right away, and yeah, I can only do it kind of approximately, but that should be just a little bit north of my 35. All right, maybe even I will put in, sorry about that, I'll put in 36 right here so I can just see it. Now, I know, right, that I'm going to hit high tide every 12 hours. So if I go over here to t equals 12 and I kind of go up here, right, maybe I'll do a little dashed line like this, I should hit high tide again, and let me label that with 12, 36. Okay? Maybe I even want that point a little bit higher. Nah, that thing looks pretty good. Now, if I'm hitting high tide every 12 hours, then that implies that my first low tide will occur after 6 hours. And what is the depth at low tide? The minimum depth is 22 feet. So over here at 6, maybe I come up here and I hit 6, 22. So my first fundamental waveform is going to look like that. Now, right, we can see now that our period is 12, half of a period is 6, and a quarter of a period would be 3. But let's now go another 12 hours out, okay? So we go to 24 hours, where we will hit high tide again. Maybe at 18 hours, right, we're going to hit low tide again. And we're going to get something like this, 24, comma 36. Let me erase that dashed line, given all it was doing was helping me locate that point. 18, comma 22. Notice that the two low tides are also separated by 12 hours, right? And that kind of makes sense given the periodic nature of this curve. And there we go. That is what my tides look like. And tides are a great example of a periodic phenomenon. Now they kind of shift a little bit here and there, and that's due to like the orbits of the moon compared to the Earth and the rotations and things like that. We're not going to get into that. We'll let your earth science, geology, etc. teachers kind of go with that. Anyway, let's take a look at letter B now. Determine the values of A, B, and K in the model. Verify your answers and sketch are correct on your calculator. Awesome. Well, we spent a lot of time in our last lesson coming up with the amplitude, the midline, and the frequency of graphs. We don't have to worry at all about any kind of horizontal shift here. And because we're starting at a maximum, we know that A should be positive. So why don't you pause the video right now and come up with A, B, and K, and also write down the final model. Okay, let's do it. Let me kind of move this out of the way. I always love starting with my K value first, you know that. So K is going to be my midline value. That is going to be all over the place here. That's going to be my minimum plus my maximum value divided by 2. That's going to be 58 divided by 2. That looks like we've got a midline value of 29. Yep, that's right. As always, I like to graph my midline value on there as accurately as I can. All right, and again, this is kind of cool from a physical perspective, right? That's telling us that the average depth in this tidal area is 29 feet deep. Okay, now we want to figure out what our amplitude is. Now I know that A is positive. Let me go back to blue. I know that A is positive, so I don't really have to go through the absolute value of A, but in technically speaking, my amplitude is the absolute value of A, and that's going to be my maximum minus my minimum divided by 2. We've talked about that that's one way that you can do it. That's 14 divided by 2, which gives me 7. And again, right, that kind of makes sense if I go 7 units up or 7 units down from that midline, right? 29 plus 7 is 36. 29 minus 7 is 22. So I have my amplitude, it's 7. Now the last thing that's in my model is my frequency, right? Now what I can definitely tell from both the graph and from the problem's description is that my period is 12 hours, okay? So we know that P is 12, make that look like a 12. My period is 12 hours, right? I know that B times P is equal to 2 pi. That means that my B is 2 pi divided by 12. You could leave it like that, or you could reduce it to pi divided by 6. Now that means that my final curve, I have no space to write, so I'm going to put it right here, is y equals 7 times the cosine of pi divided by 6 times t plus 29. And maybe I should have said d of t and not y, but literally this is now predicting the depth of the tidal water, right, at this location as a function of the hours since it was at high tide. Let's take a look at it on our calculator. We're going to want that anyway for the next part of the problem. Let's go into our graph. We're going to say we've got 7 times the cosine of pi over 6 times x plus 29. Okay, great. I don't see anything because my window is not even close to being correct. Window settings, I'm going to give myself just a little bit negative on the x-axis. We've talked about that before. And maybe I'll have my x scale by 5. My minimum, I'll put a little bit minimum there too. And what was that y scale? Let's go up to 40. and maybe make that go by tens. And I think I'm going to actually get rid of the grid at this point. I don't think I really want that on there. And there we have it, right? So I can now nicely see that it more or less looks correct. If I really wanted to nail down and see that it really is what I want, I could use my minimum and my maximum commands to find that. As always, I really love to put in my midline. Right? That kind of really gives me a great sense for the curve rising above and falling below that average tidal depth. And I have some pretty good confidence that my equation is properly modeling the physical scenario that they gave me. That's assuming, of course, that I've drawn that graph out correctly to begin with. All right. Let's put that away for right now. We're going to bring back that graph in just a moment, but let's take a look at letter C. Tanker boats cannot be in the bay when the depth of water is less than or equal to 25 feet. Set up an inequality and solve it graphically to determine all points in time, t, on the interval 0 less than or equal to t, less than or equal to 24, when tankers cannot be in the bay. Round all times to the nearest tenth of an hour. Awesome. Well, again, we're thinking in this case about this curve that we already have graphed, okay? And maybe what you might want to do at this point is think about, like, literally visualize what exactly we're looking for, try to model it with an inequality, and then try to solve that inequality graphically. Play around a little bit with this. I think you've got everything you need to solve this problem at this point, especially if you've already got that graph on your calculator. Pause the video now and go ahead and do that. Well, let's really visualize this on the calculator, right? The tankers can't be in here if the depth of water is less than or equal to 25 feet. Now, I know I've got my midline in here at 29, but let's actually go in there and change that. Not change the midline, but I'm going to actually go in and change that particular thing, nope, to 25 instead of 29, okay? So now, I know that's not the midline anymore, but I can really see that it's going to be problematic in here, right? Because that's when the tidal depth is below 25. And in here, that's when that tidal depth will be below 25, right? So if I graph that line y equals 25, I really can get a sense for this time period is problematic and this time period is problematic. And any of you that have ever traveled in a boat, if you've been in a canoe or anything like that, and you've been in a portion of water which is too shallow, you can kind of understand why this could be a restriction. Now first, let's model it with an inequality, right? We know that boats can't be in the bay when 7 times the cosine of pi over 6t plus 29 is less than or equal to 25. And we have to have less than or equal to because, like, literally it says less than or equal to. That is what it is. So there's our inequality that literally models the time period that we're looking for. Now, of course, we can go into our calculator. All right, and I'm not going to go through every single one of these intersection points, but I can go into Menu, go to Analyze Graph, go to my intersection. I really would be looking for 4 intersection points. The first one would be right there, right? So the first problematic time, whoops, that didn't help. The first problematic time would sort of occur at 4.162 hours, right? The next one, let's do the next one, and then we'll let you kind of do the other one if you haven't already. Analyze graph intersection. So now I want the sort of the end point over here. Maybe bring that up there, or maybe bring it down here. I don't know where that point should sit. There's not enough room on the calculator screen. Anyway, so all the times between 4.2 hours and 7.8 hours are going to be a problem, right? So I'm going to just, sort of take my graph out, and I'm going to label those points. So I've got, and we want them to the nearest tenth anyway, right? Round all times to the nearest tenth of an hour. So this point is 4.2, comma 25. This point is 7.8, comma 25. Using the same methodology, this point would be 16.2, comma 25. Maybe it'll make that look like a point. This one would be 19.9, comma 25. And any time in between them, right, that's where this is problematic. That's where the depth of the water is less than or below 25. So we would say all values of t greater than or equal to 4.2, less than or equal to 7.8, and all values of t greater than or equal to 16.2, less than or equal to 19.9 are when the boats are going to have to stay out of that area. Kind of cool, right? Now, in pre-calculus, you'll see ways that you can, quote, solve this algebraically as opposed to graphically. But at this level, you're not expected to be able to solve a trigonometric equation, much less a trigonometric inequality, so we end up solving them graphically, which I really like because you can really see, oh, okay, you know, that depth of the water is going to go up and down due to the tides, and there are simply these portions of time when the depth is too small. All right. Now, sometimes we're just given a model, and we need to interpret it or work with it in some way, shape, or form. So let's take a look at a problem where we're using a given model. Exercise number 2. The distance that a yo-yo is above the ground can be modeled using the equation h equals 1.75 times the cosine of pi t plus 2.25, where h represents the height of the yo-yo in feet above the ground, and t represents the time in seconds since the yo-yo was first dropped from its maximum height. All right, letter A. Determine the average rate of change of the yo-yo's height on the interval from 0, less than or equal to t, less than or equal to 0.5 seconds. You know, honestly, in this particular problem, it doesn't really matter how much you really understand about that particular model. This is an average rate of change problem, right? We are looking for the change in height over the change in time, specifically h of 0.5 minus h of 0 divided by 0.5, well, minus 0. All right, we're looking for an average rate of change. So what I'd like you to do is pause the video now and see if you can work through this. Now, if you need your calculator, and you might, to calculate h of 0.5 and h of 0, you might not. But if you need them, all right, make sure your calculator is in radian mode, okay, because these sinusoidal models are in radians, not in degrees. So pause the video now and go ahead and see if you can figure the average rate of change. And it should come out to a, quote, nice number, which is why I didn't tell you to round. All right, well, it's really important to figure out what h of 0 is and h of 0.5. We need that. So h of 0 is 1.75 times the cosine of pi times 0 plus 2.25. Now, what's kind of nice about this problem is that cosine of 0 is an exceptionally nice number, and it's actually a number that you're supposed to learn. The cosine of 0 is equal to 1. That should be 1.75. So h of 0 is just equal to 4, right? Which tells me, right, that this thing starts 4 feet above the ground. And that kind of makes sense, right? Cosine starts at its maximum. There's my midline plus my amplitude. I'm starting at my maximum. Now, where are we 0.5 seconds later? Well, now let's figure that out. H of 0.5, and again, if you did this all on your calculator, that's all right. That's going to be 1.75 times the cosine of pi times 0.5 plus 2.25. What you find in this situation is all of this is the cosine of pi over 2, right? It's 1, man, red is just coming out everywhere here, which is actually equal to 0. So h of 0.5 is 2.25. Okay. Now I have both of my y values that I need. So now my average rate of change, delta h over delta t, is going to be 2.25 minus 4, all divided by 0.5 minus 0. That's negative 1.75 divided by 0.5, and that is negative 3.5. Now, keep in mind, right, what were the units of the numerator? Height of the yo-yo in feet above the ground, right? And the denominator, time in seconds. So that's negative 3.5 feet per second. That is my average rate of change of the yo-yo's height between 0 and 0.5 seconds. It's been a little while since we did an average rate of change problem, so it's never bad to stick one of those in here and there. All right, let's take a look at letter B. Give an interpretation of your answer from A using proper units. Awesome. Well, what does that tell me? Pause the video now and see if you can figure that out. Well, obviously what's cool is that the units give us a good key. Feet per second means that we're talking about a speed or a velocity here. Both words are absolutely wonderful. Use either one of them. And the fact that it's negative tells me that the yo-yo is going down, right? Its height is decreasing. So we could say a bunch of different things here that would be perfectly good, but I'm going to say the yo-yo, which is fun to say and write out, the yo-yo is moving down at an average rate or speed of 3.5 feet per second. It's a little bit dicey to not have the word average in there. All right? So I don't know, your teacher might be more forgiving or not forgiving, so if you said the yo-yo is moving at a rate of 3.5 feet per second or down at a rate of 3.5 feet per second, that might be acceptable. But I will say this, it is not a linear function, so the average rate of change is not constant, which is why we really need that average rate of 3.5 feet per second. All right, let's kind of move on from there. Not a lot to do with our models per se, just more in terms of just, being able to do an average rate of change with a trig function. So now let's take a look at some models that are including a horizontal shift. Sometimes, that's right, they're back. Sometimes we will need to include a horizontal shift in our trigonometric models. This can lead to a non-uniqueness of the equation for the model, and we talked about that extensively in the last 2 lessons. All right, in other words, we can have many different equations that model this particular phenomena, and let's take a look at what the physical scenario is. Exercise number 3. A greenhouse is monitoring its temperature and finds that it cycles as shown in the graph below. They would like to model the temperature as a function of the number of hours since midnight. Letter A, determine the amplitude and the midline of the model. All right, so before we even do letter A, just understand, right, we're looking at the temperature of a greenhouse in degrees Fahrenheit, and along the x-axis is in the time in hours since midnight. Please note there is an axis break there because there's a lot of temperature from 0 up to 65 that I didn't want to show. It doesn't have any effect particularly on the overall problem, but it would have an effect if we put this thing into our graphing calculator, just the way we kind of think about it. Anyway, all that being said, right, you've got the graph there, and it's going to be easy enough, I hope, to determine the amplitude and the midline of this model. Pause the video now and go ahead and do that. All right, well, I'm going to actually do them in the order they actually said this time. So typically I start with my midline and then shift the screen in an unhelpful way. But this time I'm going to figure out the amplitude, right, the absolute value of A, which is going to be my maximum value minus my minimum value, all divided by 2. 84 minus 68 is 16, divided by 2, and I get an amplitude equal to 8. Awesome. Okay, now let's get the midline, right? My midline is my k value in these models. That's always going to be my minimum or maximum plus the other one. It's the average of my min and my max. That is 1, what do I have here? Yeah, I don't really want to do this in my head. That ends up being 76, so it's 152 divided by 2, or 76. I always love to have that thing graphed on there. You've heard me say that a million times. So y equals 76, meaning that that's the average temperature, right, in the greenhouse, right? The average temperature is 76. We're going 8 degrees above that to hit a maximum of 84. We're going 8 degrees below that to hit a minimum of 68. Okay, now letter B. Determine the period and frequency of the model. All right, that should be pretty easy. So pause the video now and see if you can determine both the period and the frequency. Okay, well the period is simple enough. You could either use these 2 consecutive maximums or these 2 consecutive minimum x values. Might as well, since I'm up here, I've got my period is going to be 23 minus 11, which is 12 hours. Kind of makes some sense, right? We're talking about a greenhouse. It probably fluctuates on some kind of daily basis, right, due to the sun. As well, of course, you could do the 17 minus 5 also gives you 12. So the period is equal to 12 hours. So now we know that b times p is equal to 2 pi. That means that my frequency is going to be 2 pi divided by 12, or pi divided by 6. All right, great. Fantastic, right? Now, we always do those first when we're coming up with a model, because whether we use sine or cosine, whether we shift this much horizontally or this much horizontally, these 3 numbers are going to stay the same in our parameters. Now, don't get me wrong, that's the absolute value of A. So A could turn out being positive or negative, but what we know for certain is that the amplitude, the absolute value of A, is 8. Okay, so now, let's take a look. Let me move this out of here. Let's take a look at letter C. Propose an equation that describes the cycle using the cosine function. Check using your calculator. Now I say propose an equation that uses the cosine function. There's an infinite number of equations that fit this that use cosine and an infinite number that use sine. So I guess there's 2 times infinity number that fit the entire curve. Anyhow, what I'd like you to do is pause the video and try to think about what we did in our last lesson with horizontal shifting in order to figure out one of the many different curves that could fit this in terms of cosine. Well, for this, you really have to decide whether you want the A in the model to be positive or negative. Most people like it to be positive. There's nothing wrong with a negative A, but most people like it to be positive. Now, the reason why is because cosine naturally starts at its maximum. So without a horizontal shift, cosine would be starting at 0,84. If I wanted to shift it then so that it lines up here, I would want to shift it by 11 hours. So one of the easiest ones to do here is to just say that y equals, what was our A? Our A was 8. 8 times the cosine of pi over 6 times t minus 11 plus 76. All right? And it says check using our calculator. So I say we do it. All right, let's pull the calculator out. We're gonna resize this thing entirely. So menu, doc, file, new, no, graph. Here we go. We've got 8 times the cosine of, come on fraction, there we go. Pi over 6 times, oh, no, I do not want the x yet. Parentheses, x minus 11. And now get out of this, plus 76. Okay, I don't see any graph, and that makes sense because I don't have the window sized the way I want it yet. I want, in terms of my window, my x to go from 0 to 20. Where did it go? Oh, there it is. Menu, window. Window settings, I'm going to have x go from, let's say, -5 maybe to 25. Again, the only reason I include negative x values is so that I can see the y-axis. My y's, let's see, I think I'm going to have those go from like 60 to 85. And, whoops, nope, let's try 85. What do I want my scale to be? By 5s? Sure. Let's go down here and scale it by 5s. And there we've got our curve. All right? And that definitely looks right. Right? And again, we're kind of ignoring this section of it. We're just taking a look at this section, and that is exactly what I see here. If I really want to ensure that it is really right on the money, right, one thing that I could do, let's say if I went into my menu and I analyzed graph, let's say I looked for a maximum, right, I could easily just try to nail down this maximum. Oh, it is just not going to work for me here. There we go. And by doing that, I can really see that yes, I've got the right maximum at 1184. If I really wanted to be certain, I could even find that minimum, make sure that it corresponds to 17,68. But given the way that the graph looks like that, given the fact that I have that maximum in the right place, I have some pretty good confidence that I've got the right equation, or one of the right equations. Okay, now let's go back into my full screen and let's talk about letter D. Propose an equation that describes the cycle using a sine function. Check using your calculator. All right, now I always find for myself that the sine function is a little bit harder to model with, which is a bit ironic given the cosine function is sort of based off of the sine function. But you see, the cosine function starts at a maximum. And even if I wanted a minimum, that would be easy enough because I could just make the 8 negative and shift it 5 units. All right, so a great equation would have been -8 times cosine pi over 6 times t minus 5, right, instead of +8 and t minus 11. So with sine, right, I want to find where the curve intersects the midline. That's right here and right here. Now, sine naturally rises out of the midline if it hasn't been shifted at all. So if I want the a value to be positive, that's a big if. If I want the a value to be positive, then I need to find that x coordinate. Now remember, the key to finding that x coordinate will be to know what a quarter of the period is. So the period, right, was, was 12, and a quarter of the period is 3. So if I look at that x value, right, and I want this x value, that'll just be 11 minus 3, and that'll be 8. Great. I got a double 8 again. I got an 8 there, and I have an 8 in there. Anyhow, so if I just want to shift the curve, which would have naturally started without a horizontal shift here, and I want to shift it all the way over to here, I will have to subtract 8, okay? In which case, I would have y equals 8 times the sine of pi over 6 times t minus 8 plus 76. 76, I say it, and then I write down 75. Very strange. But I love me some 75, right? It's such a nice number. Anyway, just to verify this quickly on the calculator, one of the great things here right now is I can actually go in, I can go in, put a new function in, and I don't need to change my window at all. I just go in, grab sine, put in my fraction, pi divided by 8 times x minus 8 plus 76. Let's see if we get it right this time. Enter. Oh my goodness. Thank you, Joey. Here I'm like, well, that doesn't look right. Let's go up and edit that thing. Oh man, what was wrong there? Oh, pi divided by 8. I got the period wrong. And it's kind of cool because you get, I have to literally get over to the fraction, otherwise it will misinterpret it. Pi over 6, there it is. Okay, and I'm reassured that it's correct because it lies right on top of the other one, right? These two equations, right, are two of an infinite number that correctly describe that curve. You know, which one that you actually want to use, that's entirely up to you. All right, let's go back in here, and let's now take a look at letter E. An office next to the greenhouse has a temperature given by the function y equals -3 times the cosine of pi over 12t plus 71, where t also represents time in hours since midnight. Write an inequality that represents all times on the interval 0 less than or equal to t less than or equal to 24 when the office temperature is at least as great as that of the greenhouse. Then solve the inequality. Round all times to the nearest tenth. Fantastic. So this isn't all that different from the problem where we had sort of the tidal depths and whatnot. What I'd like you to do, maybe you should start by graphing this one. You may want to delete one of those two. You know, I have got the sine one sitting here, but the cosine one works just as well. It doesn't matter. Or if you had different curves that were correct, you could use one of those. It's that infinite thing again, right? First, try to model with using an inequality, then try to find all the times by graphing the thing, you know, along with one of the correct versions that we have from the previous problem, and see if you can find those time intervals. All right, well, we want the office temperature to be at least as great as the greenhouse. In other words, the inequality that we're trying to solve here is -3 times the cosine of pi over 12 times t plus 71 is greater than or equal to, if I use this particular version, 8 times the sine of, I'm not going to be able to fit it, divided by 6 times t minus 8 plus 76. Wow, okay, sorry, that got a little messy there. That's a plus 76. Anyway, you want this function to be greater than or equal to this function, or, you know, you could use this one as your model, or if you had an a that was negative and you had a correct model, that was fine as well. All right, now we want to be able to model it, right? In other words, if we graph this particular function, we get something that looks like that, okay? And remember, we're looking for where this thing is greater than or equal to our original curve. In other words, we want this time period and this time period. So just like we did with the tidal depths, of course, what you're going to do in this situation is you're going to find those intersection points, and those things happen to be, well, I don't have the y-coordinates, but I do know that the x-coordinates are at 3.6 and at 8.9. This one intersects at 14.7. I really should have the exact intersection point sitting on there, and I don't. I apologize for that. And 18.6. And so I can say that this is valid for the time period that's between 3.6 and 8.9 hours, and for the time period that is between 14.7 and 18.6 hours. All right, so very, very similar to the problem that we did on the tidal depths, right? The big difference is that this isn't a horizontal line. This is itself a sinusoidal curve, right? And it kind of looks neat up there. It's a sinusoidal curve that clearly has a smaller amplitude, but a greater period. Not that that matters that much. Okay, so let's wrap this thing up. There are a myriad of physical things that can be modeled using sine and cosine curves, some of which we didn't even touch on, like sound waves, light waves, X-rays, infrared rays, all sorts of cool things from chemistry and physics, right? When you pluck a string on a guitar and it goes back and forth, right? The frequency of that motion gives you the note that's being played. The amplitude gives you the volume that you hear. When you have a light wave, the frequency actually gives you the color, and the amplitude gives you sort of the brightness of the color. All right? So there are all of these wonderful situations in the real world that are wave phenomena, from electrons moving around the nucleus of an atom, to light that we see coming from the sun, to the sound that we hear when we listen to music. You know, all of them are wave phenomena, and all of them can be described and understood using what we've looked at in the last 4 or 5 lessons. So I hope if you've ever wondered, what is this ever going to be used for, you don't have to ask that about what we've been working with for the last few lessons. Now, the next few lessons, we're going to take a look at some additional trigonometric functions, like the tangent function. Where did that thing go, right? You know, you saw that a lot in geometry, and we're going to take a look at that in our next 2 lessons, and then in our last lesson in this unit, we're going to take a look at 3 additional trigonometric functions, just to give you a little bit of groundwork for when you go into pre-calculus. Plus, they're also required at this level, but just a little superficial examination of them. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.